Okay, so in part 8, we're talking about sheet metal bending operation. Now we talked about the cutting in the previous section, and that's the process of forming the shape of the metal according to the mold we are going to have. Okay, so we can see here in the two images in front of you some of the definition for the operation. We're always going to have a neutral axis in any shape. And when we're going to start to bend the sheet metal, we're going to have two areas of stresses. From the outside, we're going to have the metal to be stretched. From the inside, the metal is going to be compressed. Through the neutral axis, this value is going to be equal to 0. So we need to calculate some of the parameters like the radius of the bending, the thickness of the plate, the location of the neutral axis, and the width of the plate I would like to bend. You can see that the alpha, which is the angle of the shaping, is going to be equal to the same value if we're going to get it from the other side. So the pro is going to be straining sheet of the metal around the straight axis to take the permanent bend, and the metal on the inside of the neutral axis is going to be compressed. The metal on the outside of the neutral plane is going to be stretched. Touch all the sheet metal bendings we have. The easiest one and the most common one is going to be the V bending, which performed with the V-shaped die. As you can see here, this is the die, has a V shape, and the punch is going to have the V shape. And then simply again to put the plate, press it with the certain force amount by the punch, and we're going to have the 90 degree, or it's going to be any degree of the bending according to your work. Performed with the V-shape die, by the way, it can be also with the rounded one. Low production rate performed on the pressure brake, and the V dies are simple and inexpensive. The edge bending, which performed with the wiping die, as you can see here. Okay, now that's the wiping dies. Okay, and have higher production rate. Pressure pad is going to be required, and dies are going to be more complicated and costly. The stretching during the bending, as we mentioned, if the bend radius is going to be small relative to the stock thickness, I mean that the R is going to be quite small relative to the T value, then the metal tends to stretch during the bending. Important to estimate the amount of stretching, so the final part length is going to be equal to the specified dimension. The problem we have with this operation is that to determine the length of the neutral axis of the part before the bending operation. The bend allowance formula tells me that the allowance value or the bend allowance AB is equal to 2 multiplied by the pi multiplied by the bend angle divided by 360 and multiplied by the addition of the radius, bend radius plus the value of the K factor and multiplied by the thickness of the plate or thickness of the stock. Okay, so usually the K value will have a range. So if the radius is going to be less than 2 times the thickness, the K value will be used to be 0.33. If the radius is going to be more than or equal to 2 times the thickness, then the KVA value is going to be equal to 0.5. One of the problems that we have with the sheet metal bending is going to be the spring back, which is increases in the include angle of the bent part relative to the included angle of the forming tool after the tool is going to be removed. So if you can see in this video, when you're going to remove the force, the part will be having the spring effect. The reason behind of the spring back is that when bending pressure is going to be removed, some elastic energy will be remains in the bent part, and this will causing it to recover partially towards its original shape. The spring back results in the decrease in the bend angle and an increase in the bend radius. And during the bending, the work is going to be forced to take the radius RT and the angle alpha B prime, or the angle of the bending tool. When we're going to remove the punch, the work is going to be spring back to the actual radius and the actual bending angle. To calculate the bending force, the maximum bending force is estimated as the following equation. The force of the bending is equal to the KBF value, which is once again a factor for the V bending, range between 1.33 for the edge bending up to 0.33, and multiply by the TS, which is the tensile strength of the sheet metal, multiply by the width of the part, and finally multiply by the thickness square. Okay, and that's to be divided by the diameter of the bending, or the D, which is 2 multiplied by the R. The die opening dimensions, as we remember in the case of the bending, we are going to have some, in the cutting, we're always going to have clearance. So the die opening dimension for the V die and for the widening die is given in this photo. So you can see that the D is going to be equal to the 2 multiplied by the R, or 2 multiplied by the radius of the bending we have. And in the case of the the other types of the bendings, we're going to have that the clearance is going to be equal to the 2 multiplied by the radius of the bending. The other operation is called the drawing. So you remember that we talked about the bar and the wire drawings. This drawing is going to be drawing for the sheet to take the shape of the mold that we have. So a sheet metal forming to make the cup shaped or the box shaped or any other complex curved hollow shaped parts. The sheet metal blank is going to be positioned over the die cavity, and then it's going to be pushes the metal into the opening. The products can be the beverage cans, the ammunition shells, the automobile body panels, and so on. Also is known as the DB drawing to distinguish it from the wire and the bar drawing. So you can see in this diagram, we're going to have the blank, which was cut it from the blanking operation that we mentioned earlier, and then we're going to put it in between the die and the blank holders, and then we start to operate the punch. So the punch is going to be moving downward, and it's going to be push the plate in order to take the shape of the die, and then we can take the part out, which is going to be a cylindrical hollow shape. The clearance we have in the drawing is going to be usually equal to 1.1 or 110% of the stock thickness. So once again, if I'm going to have the thickness of the base going to be 10 millimeters, the clearance should be equal to 11 millimeters. In other words, the clearance is about 10% greater than the stock thickness. Test of the drawing feasibility is going to be, first we have to do the drawing ratio, check the reduction, and thickness to diameter ratio. The drawing ratio, or the DR, is going to be most easily defined for the cylindrical shape, or for example the cup, by using the equation that the DR, or drawing ratio, is equal to the diameter of the blank and divided by diameter of the punch. And that definitely should be more than 1. The indicates stability of the given drawing operation for the upper limit. This drawing ratio should be equal to or less than 2. We said that the minimum we're going to have is going to be 1.1. The reduction, which is defined by the cylindrical shape to be equal to diameter of the blank minus diameter of the punch divided by diameter of the blank. Usually with the R value should be less than 0.5. We have thickness to diameter ratio, or the T divided by the dB, where thickness of the starting blank is going to be divided by the blank diameter. Desired value for the thickness to diameter ratio should be greater than 1%. As the value for this ratio is going to be decreases, tendency for the wrinkling is going to be increases. The blank size determination can be also done for the final dimensions of the drawn shape to be correct. The starting blank diameter, or the dB, must be right. Solving for the dB by setting the starting sheet metal blank volume to be equal to the final product volume. Now, how this will help us? Okay, So the final volume of the products is going to be easily calculated. I know the thickness, and I choose the diameter to give me the same volume of that part. To facilitate the calculation, assume we have negligible thinning of the part wall, because actually it's going to be thinned. If I can stretch something, the thickness is going to be reduced, but to make it easier, we're going to consider that we have a cylindrical shape, we have a base, we have the area for that base, we can check the volume of the base, we can check the volume of the cylindrical wall, we add them together, the same volume should be given for the blank. Shapes other than cylindrical cups can be done with the deep drawings operations. It can include the square rectangular boxes, the stepped cups, the cones, the cups with the spherical rather than the flat bases, the irregular curves forms as in the automobile body panels. So that will be the part number 8. And we're going to move for the other operation, which also can be done on the press machine in the part number 9.